why did you display this one?
This unit came on the market about 7 years ago.
Okay.
It's not too old, 7 years now.
Okay.
And this is the best phase noise analyzer
Currently
on the
available.
Market, yeah.
Okay.
On the market, yeah.
Okay.
Not just from us, worldwide.
Impressive. Impressive. Yeah. And hello, my friend. What is your niche? What is your quantum technology? What's your application?
Do you know about us?
Quantum software lab.
Software lab.
Element 6 is supportive and inclusive. So these are elements, the natural elements, or what kind of element are these ones?
So we're called element 6 because of after carbon straight out.
Yes. Okay.
So for this particular defect we need a microstructure. We essentially take 2 carbon atoms, remove them, and then in one of the holes we put a nitrogen atom. So it gives me an extra vacancy.
Oh, thank you. Timing application, yeah.
So we have a whole load of single frequency lasers.
Yeah.
So these all fiber lasers.
Okay. And what about for quantum communication? Do you like a very, very coherent one, like probably?
Yeah, so they are, our coherence product has very long coherence length.
So guys, if you're watching this channel, I'm just here showing you the quantum things that the UK has been up to in terms of quantum research. That's what they are showing us here. It's called Quantum Showcase in the UK, in London. So that's where I am right now and trying to see what people have been up to in terms of quantum research. So if you want something to eat, so we are inside, guys. These are some of the things that's happening here. I don't know what's going on up there. I think maybe people are eating or something. A lot of people, guys. All the quantum heads are here. I have met some of my colleagues, but I didn't show them on the vlog because I don't know how they feel about recording them, but yeah. Hello, my friend. What is your niche? What is your quantum technology? What's your application?
Do you know about us?
Quantum software lab.
Quantum software lab.
No, not yet.
Okay. Do you know about University of Edinburgh? Up in the north.
Yes, yes, yes. yes.
Okay. We are the largest academic research group
Yeah,
focused on quantum software and algorithm.
yeah.
So we're based in University of Edinburgh.
Edinburgh.
And we founded the lab in collaboration with the National Quantum Computing Center.
Okay.
Yeah. So our director, Elham,
Okay.
Professor Elham Kashefi, at the same she is at the same time
Okay.
the NQCC's chief scientist.
Yeah.
So we have a very strong partnership with NQCC right now.
Okay.
So we have different working groups, all of them focused on quantum software and algorithm, theoretical stuff rather than quantum hardware.
Yeah.
It makes us kind of a unique research group. Most of the other research groups across the UK, they focus mainly on hardware.
Hardware, yes, yes.
But we are based on School of Informatics, so we basically working on the software and theoretical part.
Oh, okay.
And our members have different backgrounds. Some of them are coming from physics, some of them from computer science, some of them coming from mathematics.
Yeah.
And we are trying to somehow cover most of the topics related to quantum software.
Okay, okay.
We have our members, I think we have around 54 researchers, including PhD students, postdocs, and other academics.
Yes.
And we're working on hybrid cybersecurity, quantum cryptography, quantum machine learning, complexity theory, quantum benchmarking and verification, and also HPC integration, quantum simulation and emulation.
Yes, yes.
Also quantum error correction and quantum algorithms in general.
Okay, okay, okay.
Yeah, so, and also we are next year, we are organizing this festival of quantum events, Quantum Fringe.
Oh, okay.
Yeah.
It's happening at the University of Edinburgh.
It's in Scotland.
In Scotland,
Some of them is in Edinburgh.
Okay.
At the moment we have 4 pillar events.
Yeah.
A summer school in Isle of Skye that
Okay.
organized by ICMS, which is in Edinburgh, and LMS
Yes,
in London,
yes.
and
Yeah.
Heriot-Watt University.
Okay.
And FQC is a workshop, is a conference workshop in Edinburgh, co-organized by Royal Holloway University.
Okay, okay.
It's focused on foundations of quantum computing.
Yeah.
Also, we will have a one-day packed workshop, the 8th day.
Yeah.
We're bringing the industry partners and
Yeah.
also the academics to find the use cases that we actually can address.
Exactly, yeah.
And also, we will have a quantum hackathon, UK quantum hackathon, which is organized by AQ.
Oh, the hackathon, yeah. That's very interesting, yeah.
So all of them are happening in the Scotland base.
Okay, okay. So you are basically just focusing on software or...
Yeah, basically we are focusing on software rather than hardware. Because
Okay.
let's say that you will have the fault-tolerant quantum computer in 1 year.
Yeah.
So you should be able to run something like that and implement some algorithm.
You are right, yeah. Okay.
Also, this is our CDT program. This is the educational program of the lab.
Okay.
Which it's a 4-year PhD program, and
Okay.
each year we will absorb around 15 students.
Yeah.
And most of them will be based in Edinburgh, but Heriot-Watt University, UCL, Oxford, and University of Strathclyde, they
Yeah.
are our partners that some students will be based in.
Okay. So we will give you all of this so that I can just have it. Okay. Thank you very much. Thank you very much. Yeah. Are you also part of the team or?
I'm here for asking questions.
Okay, I'll leave you for that. Thank you for your time. Yeah. So guys, that was some software companies from University of Edinburgh. I think it's in Scotland or something. Yeah.
I was trying to remember an event at the Swiss Embassy.
So what's your interest in quantum technology?
So,
Yeah.
we grow diamonds for a wide array of different applications.
Yeah.
One application we're particularly interested in is,
Yes.
do you know anything about nitrogen vacancy centers?
National?
Nitrogen vacancy.
No.
So it's a type of defect that you have in diamonds that turns it pink.
Okay.
And
It turns pink when you do what?
when you form this defect.
Okay.
So it has particularly interesting qualities for sensing capabilities.
Okay.
You can take this if you would like to.
Yeah, hopefully, yeah. Element 6 is support different include 6. So these are elements for the natural elements, or what kind of element are these ones?
So we're called element 6 because of after carbon, because that's what diamond is made out of.
Yes. Okay.
So for this particular defect, we need a nitrogen. So we essentially take 2 carbon atoms, remove them,
Yeah.
and then in one of the holes we put a nitrogen atom. So
Yeah.
it needs to be next to a vacancy. So when we have that, it has particularly interesting applications with regards to like sensing, because it's particularly sensitive to like magnetic fields. It has like
Okay, I see. Oh, it's very sensitive to magnetic fields, and then it can be used as a sensor.
yeah.
It's a quantum sensor, you mean?
Yeah, exactly.
Okay.
And because of this specific defect, it has another thing. So we're also quantum communication. as like
Okay.
a piece of
Well, that's interesting. Yeah. I'm more interested in communication. Yeah. Okay. And those are very. Okay. Okay. So do you make these elements within the UK or?
Yeah, so we brew all of these diamonds.
Yeah.
So we have 2 different methods of growing them. We have high pressure, high temperature, which is more like the traditional way you make diamond.
Yeah.
And these are all made of chemical vapor deposition,
Yeah.
where you decompose a gas and sort of grow the diamond ground up, so layer by layer. It gives you a lot more control over what the diamonds contain, because you just need to add in the gas. So this is very high purity, so we've tried to grow it with as few impurities as possible.
Yeah.
And then these at the back are more your nitrogen dopes, so we add nitrogen as a gas for the formation of these diamonds. And then to make the vacancies, we irradiate them to like knock carbons.
The carbons out. Yeah. Okay, that's interesting. Have you find like apart from sensing, what's other applications said communication? And
the idea is that the diamond will be really useful in quantum computing as well.
Yeah.
The nitrogen vacancy center itself has like a few limitations when it comes to that, but other defects and stuff are possible and might be worth looking into further things here. It's like a qubit.
Yes. And timing. I'm actually from the timing from NPL. We do a lot of timing. How is this application going to be used in timing, for example?
No, I'm not too sure myself. Matthew might be the better person to kind of direct the answer to. Sorry,
Okay.
I'm slightly new to the company, so I'm still.
Oh no worries. Yeah, but I think there should be something in your magazine. Can you? Yeah.
So we've got like a few different ones. This one talks about navigation, anomaly detection, and sensing.
Okay. So do you have anyone that talks about communication and probably timing? I'll be interested. Communication and timing. I'll be interested in that one. Yeah.
Circular scanning, spintronics.
Okay.
We've got a lot of them have. Well,
Oh, thank you. think one of my colleagues is working here. Yeah, guys, there's so many things going on here. It's more of quantum technology. All of this quantum technology. So
I just want to take the picture.
this quantum wine, or
What is the demonstration?
This is our standard hydrogen detector. It's perfect with it.
reflection. I think I'm familiar with these guys. Reflections. Rotten Swartz. You are very famous guys.
Pardon?
What's your next, your current technology term for spectrum analyzers?
Yeah,
Higher performance one.
phase noise analyzers here. Phase
Yeah.
noise for measuring the phase noise of these analog signal generator.
Okay. What's the sensitivity of this one, the one on top there?
This is the analyzer, this is the generator.
Yeah, I'm interested into the analyzer there on top there.
The analyzer on
Yeah.
top is what's called the FSWP,
Yeah.
and we're measuring a 10 gigahertz signal at various offsets.
What's the maximum frequency you can take with that one?
For this one, it's 26.5 gigahertz, but we've also got a 50 gigahertz unit. And if you want to go higher, you can have harmonic mixers, and you can get up to 325 gigahertz.
I see. Currently, I see you are testing this generator here, isn't it?
Yeah,
What's the phase noise right now? Like, let's say at one hertz.
well, 1 hertz is way on up here. So we've got 100 hertz, which is minus 96.
Oh, okay. Yeah. It's quite good, very good. Yeah. It's a good generator. What's the maximum frequency? 20 gigahertz.
This one is 20. We go up to 67 gigahertz in total.
Okay.
This one is 20.
20, I see. Yeah. Do you have anything like in the megahertz range, like 100 megahertz?
Well, this one starts from 1 megahertz. This can do phase noise analysis from 1 megahertz.
Okay,
But
okay.
you need an 8 gigahertz version, 1 megahertz to 8 gigahertz.
Okay. Because we are actually having some 10 megahertz frequency that we want to test within our lab.
You can do it on this, but it's they may be more expensive than a lower frequency phase
see.
noise analyzer on the market.
I see.
This is more RF microwave. But yeah, you could measure it on this.
Okay. And what about more like for telecom application, signal analyzers for telecom application?
Well, you can do signal analysis on here.
On this one
This
as
is a
well, okay.
spectrum analyzer as well.
Yeah.
And you can do vector signal analysis here.
Yeah. IQ analyzer. I see
IQ
that.
analyzer, yeah. We also have another unit, it's called the FSW, and that's more dedicated for wireless comms, Wi-Fi.
Okay.
Yeah.
Okay. Yeah. Oh, I see.
Same chassis.
Yeah, it seems. Is this like your latest technology, or why did you display this one? Is this like?
No, this unit came on the market about 7 years ago.
Okay.
It's not too old, 7 years now.
Okay.
And this is the best phase noise analyzer
Currently
on the market,
available,
yeah.
okay.
On the market, yeah.
Okay.
Not just from us, worldwide.
Impressive.
Competitors.
Yeah. And did you have phase noise, phase comparator or something like phase comparator?
Yeah, there is something coming out soon. It's a phase reference.
Yeah.
For the phase
Reference. Yes.
And we will have a phase reference for the FSW.
Yeah.
And we'll have a phase reference for this vector network analyzer.
Yeah, I was asking for this one, vector network analyzer.
And we'll have a phase reference coming out very soon, actually.
Okay. It's like in the pipeline of getting developed or something.
Should be out soon.
Okay.
Should be released soon.
That's good. Yeah, give me your.
You got a business card?
Unfortunately not, but I'm from the National Fiscal
NPL,
Laboratory,
yeah.
NPL.
Who do you work with?
I work with the JO. I'm from the optical fiber link.
You work with who?
Yeah. JO, Jake Olivier.
Jake Olivier.
Yes, and you know again Rachel. Rachel.
Not sure. Yeah.
Not sure. And you know who's this?
You see the head of the group?
She's here.
Jake Olivier.
That's my line manager. That one.
Ah, yeah.
My
Okay.
line manager. Yeah.
Yeah. Have you need any information? Please get in touch.
Yeah, I will get in touch. Well, where's your office based? Like here in London?
Fleets in Hampshire.
In Hampshire.
Yeah, about 20 miles from NPL.
Oh, quite
Very
far.
close.
Yeah.
Well, 20 miles is not far.
If you make by drive, yeah.
Yeah, drive. It's about less than an hour. 45 minutes
Okay.
in the car.
Okay.
And not too far at all.
Okay. Yeah, we have a lot of equipment in our lab. That's why I was interested to see and see what's going on. This is more for communication purpose, network analyzers.
Yeah, you're looking at power measurements, you're
very
looking at
useful, yeah,
time
power
domain
measure,
measurements. Yeah,
What are you testing
it's an
here?
amplifier. Yeah, USB amplifier.
Oh, wow.
You use it for that. Antennas, mixers.
Impressive. So guys, this is where the quantum people are. Laser for quantum, or NKT photonics, very popular branch. We used to have one of their lasers in our lab, the university. Very coherent laser. I like your brand, man. It's very nice.
Thank you.
What's your higher performance laser you have right now?
So we manufacture lasers.
Yeah, I know. I think I have one of your system in my lab. Yeah. Yeah. Should be something similar to this one that we bought, but yeah. Is there any improvement from the previous design to this currently one?
So we have a whole range of products. So what's your application? What do you use?
Mainly for timing.
Okay.
Timing application, yeah.
So we have a whole load of single frequency lasers.
Yeah.
So these are all fiber lasers.
Okay. And what about for quantum communication? Do you like a very, very coherent one, like probably?
Yeah, so they are our coherence product has very long coherence length. So it's low noise, long coherence length. That's its reason for existing.
Yes. Wow. You don't do like compact ones, like some.
So this is a.
Oh yeah, something like this, yeah.
So this is a fiber laser.
What's the line for this one? Approximately.
Let me check.
Yeah. Yeah, guys, these are NK14 guys. Very, very popular in terms of laser design. Very good company.
I need to check the line width.
Okay. And the wavelength, they are all 1550 or around there?
There's a number of wavelengths. So they do 1550, but we've got a whole range of modules across 1550, 1064, 1762.
Okay.
And then there's a whole range here of the different transition bands.
Oh, I see. Oh, it's strontium, rubidium, ytterbium. Oh, okay. Very nice. So mostly for us, I'm from NPL. We are interested into strontium lasers and ytterbium. We are currently developing a ytterbium quantum quantum clock, and so I think one of my guys will be able to get in touch with you and try to see if they can source some of these lasers. Yeah.
So Mark's the right guy to talk to about that.
Okay. Hi Mark, how are you?
How you doing?
So sorry, I'm recording this for me to go through and see what I can figure out.
Okay, no worries.
We are having like from NPL, we design optical clocks,
Yeah.
Quantum clocks, but mainly strontium and ytterbium. Is there any lasers that you have currently in the market which can cater for that one?
Yeah, absolutely.
Yeah.
So we start off with
fiber lasers.
Yeah.
And everything we do starts in the infrared. So we have 3 material systems for fiber lasers. One is erbium, ytterbium, and thulium.
Yeah.
And from that we can get 1 micron, 1.5 micron, and 2 micron lasers. And then we can amplify up to multiple watts.
Okay.
I think maximum 15 watts.
Okay.
And then we can also do frequency conversion. So we can mix and match different wavelengths, or we can do second harmonic generation in a box like this.
Oh, okay, for you. This is this box.
And if you try and lift this, it's really heavy. It's because it's like a single piece of metal. Everything's glued down.
Can you hold for me this one? Lift it. Oh, wow.
It's like lead.
Yeah, it is. Yeah.
It's crazy.
It looks like it's a heavy, I mean like a lighter thing, but it's quite heavy, yeah.
The reason it's so heavy is because everything is like super robust on mounts that have 0 alignment, and then it's temperature tuned to allow stable output from the visible ports.
Yeah.
And basically you can get almost any wavelength across the visible spectrum by mixing the few wavelengths.
This is something like a frequency comb or something like that?
So we don't make frequency combs, but we have a company that's also owned by Hamamatsu called Menlo Systems, and they make combs.
Menlo, yeah, we have some Menlo combs in our laboratory.
In some of their systems they have reference lasers like this.
Okay.
We can also, in this system here, the Coherus acoustic, we can add modulation in the form of an acousto-optic or an electro-optic modulator.
Yeah.
And we can do the modulation in the infrared, which gives us a lot more options for our components, or we can do it in the visible.
Okay.
So lots of options, a really flexible system.
Do you have like so quantum future is here.
Business incubation center. Startups. There's funding. Is that of interest? Frictional security projects would be interested to participate. Yeah,
Yeah, I was going to say, well, I guess it makes more sense. Oh, there's not a project I do where they're so proud to say
This student has a prosperity partnership that we've got with. So we're building a gravity gradiometer and optical clock with a lift stabilization.
KT, nice.
Photon source.
Yeah.
Oh.
That's a live photo of what's inside the box.
So all the photons are inside here?
Yeah, this is a microscopic image.
Okay.
The device we are putting.
So what's the operation of this and what does it do? What's the function? What's the application for this one?
So this is a entangled photon source.
Okay.
And we have C-band quantum dots producing entangled photon pairs.
Okay. So you mean like yes, for application for like quantum computing or something like that, or?
It is a potential source for quantum computing, but mostly we are focusing on the communication.
Quantum communication, okay.
Exactly.
Okay.
So here we're demonstrating the vision of a quantum internet.
Yeah.
So we have our quantum source and then sending
through the fiber.
Photons, through the fiber to our SPAT.
Okay.
So everything is wavelength.
So how do you quantify the performance of this system? Like is in bit rate or what's the how do?
Yeah. So this is our very first prototype.
Yeah.
Of the QLE module.
Yeah.
And the rate is not to the spec of the communication technology at the moment.
Okay.
We're working on brighter devices, which give us higher rates.
So you have a quantum detector here and this setup. Where's it?
This is a factory itself. Maybe in this metal box.
Is that like a photodiode or what?
That one is like
single photon avalanche diode.
Okay. So it's able to differentiate between the two type of photons coming to it.
Exactly.
Okay. And what's this on the spectrum analyzer?
So this
Oscilloscope.
we also still get signals coming from the spectrum.
Yeah.
So these red curves representing the gate signals that we are supplying to the SPAT.
Yeah.
The blue traces is the single photon signals that are picking up by the detector.
Okay. Awesome.
And then Rose, do you want to talk more about the SPAT?
Yeah, so I work with single photon detectors. This is my project.
Yeah.
So inside we have a little APD chip with a tech.
Again, what is inside here?
This is a little InGaAs indium phosphide diode.
Indium phosphide,
Yeah.
okay.
Inside this box
Yeah.
with a tech. Basically, we can cool this down to minus 50.
Yeah.
At the moment, we're applying a 10 megahertz gate, but we can go up to 1 gigahertz.
Okay.
And like Janine says, these are basically, each of these is when the SPAT is reacting to a single photon, and it's
Okay.
avalanching.
Avalanching.
Can you do with the kids being like,
So are you planning to do this like in terms of quantum communication in the future, like application?
Yeah, so the idea is to move these butterflies towards being used within our QKT systems.
Okay. Awesome. Is that like a PhD research or what's that? Part of your PhD or?
So I started at my PhD. I now work full-time at Toshiba.
Okay. Okay.
I can give you my card if you'd like.
Yeah, definitely. All right. Toshiba. It's a Japanese company, huh?
I know, yeah.
I did my master's in Japan, by the way.
Oh, right.